A commonly used application of vectors is in projectile motion in physics. Projectile motion involves using a set of equations called parametric equations. And actually a parametric equation, singular, involves a pair of relationships where x and y are both related to a third variable called t. And it's called t because it usually represents time in application problems. So here are my two equations. Here's a table of values that goes with these equations, and here's the graph of this relationship. So let me show you how this works. Let's say, for example, t equals 3. So in other words, maybe t represents 3 seconds. So 3 seconds after this motion starts, or whatever it is that starts, where is x and y? So we're going to say x of 3. Notice x is a relationship involving t, is 2 times 3, which is 6. Y of t is y of 3, which is 3 plus 4 times 3 minus 3 squared, or 3 plus 12 minus 9. 3 plus 12 is 15, minus 9 is 6. So this corresponds to this row on the table. When t is 3, x is 6, and y is 6. And I could get any other row on this table by substituting various values for t into these two equations and getting x and y pairs for each value of t. Now notice on the graph here, this is just a regular graph with x on the horizontal axis and y on the vertical axis. And you might think, well, where is t? Well, t doesn't actually show up on the graph. T is just kind of an underlying variable. T is how we get x and y, but it doesn't show up on the graph. So we would say, for example, when t is 0, the position here is the point 0, 3. So this point right here, 0, 3. When t is 1, we are at the position 2, 6. When t is 2, we're at the position 4, 7. When t is 3, we're at the position 6, 6. So this is the position here that we just calculated when we use the table. At t is 4, we're at the position 8, 3. And when t is 5, we're at the position 10, negative 2. So basically, this set of equations, this parametric set of equation, shows position xy at a certain time t. Oops. Certain, here we go, a certain time t. So this is really an unusual situation in where the input is t, but the output of the function is actually a pair of values. So the output is actually the xy. Okay, so for each input t, we get an output that is actually a pair of values, a position on the graph. And this is what a parametric equation is. Now, let's look at why it's important to use a parametric equation in projectile motion. Projectile motion involves shooting, launching, throwing something into the air. That's what projectile motion is. We're projecting something out. And in this case, we're shooting a cannon. And let's say the cannon is facing directly horizontal when the cannonball is shot. Now, if we were in outer space and we shot a cannonball, it would just keep going straight because there's no gravity associated with a planet or a star or anything to pull it down. If we were kind of in a middle of outer space, not close to a planet or a moon or anything, the ball would just keep going. If you've ever seen pictures of astronauts in a spaceship and they throw something, it just keeps going in the direction that they throw it straight. It doesn't curve down like we would expect on Earth. What we know is going to happen is if the cannonball is shot straight out, it's going to curve down and eventually hit the ground. If there was no force, if we just took the cannonball and dropped it, it would drop straight down like this. So what we have is motion is actually affected in two different ways. There's the horizontal motion of the cannonball, which is constant. So the horizontal motion has constant velocity. If it were unaffected by gravity, it would just keep going the same amount of distance every increment of time, and it would keep going in the same direction. However, the vertical motion here, which is represented by the yellow balls, vertical motion is not constant because it's affected by gravity. So that's this row here. So you can see that for every equal increment of time, the ball is speeding up as it approaches the ground. It's going faster and faster. In other words, it's moving a larger distance for each increment of time as it moves down. When on Earth, the acceleration due to gravity is negative 9.8 meters per second squared. In other words, for every meter, for every second of time, the ball speeds up another 9.8 meters. So it keeps getting faster and faster and faster and faster as it moves down, which is why you could drop a penny from a skyscraper, and by the time it hits someone on the head on the sidewalk below, it could kill them because it's going so fast. Now, when we put the two together and we have, this would be our x of t, and this would be our y of t. If we put these together as a set of parametric equations, the result is a parabola. So projectile motion results in parabolic movement. Okay. So this is going to be just as a little introduction then to what we're going to look at. We're going to look at then in our next video the set of parametric equations that specifically describes projectile motion.